So, Dan, I was dropping my brother off at college recently at the University of Michigan, and we went to a nearby restaurant that was outside of Ann Arbor in one of the neighboring towns. And the restaurant was in this building that actually used to be a brothel. And so the woman who owned the restaurant was telling me and my family these stories about the ghosts that haunt this old brothel building. And she told us that there's a video evidence of one of her cleaning staff cleaning the basement after hours, and there being a shelf of salt and pepper shakers that just flies off the counter. And then the cleaning staff person screams and runs out of the shot. And so I think that that's pretty good evidence that there was a ghost nearby. Are you convinced?
No, I guess I'm not. I'm going to, channel my inner Carl Sagan and say that truly exceptional claims like ghosts exist require exceptional evidence, and I don't think the evidence is particularly exceptional at all.
So, that being said, we're going to talk about something possibly crazier than ghosts, an invisible kind of matter that we've never seen or detected that we think exists in larger quantities than any kind of normal matter. And we think this stuff is all around the universe. Dan, are you really convinced that there's all this invisible matter?
Yeah, you're talking about dark matter, and yeah, I think it is exceedingly likely that dark matter exists and is extremely abundant throughout our universe. And the evidence is just overwhelming.
Okay, cool. So let's go through that evidence and see why it's so much better and stronger than that ghost evidence. Maybe I should say I haven't actually seen that ghost video. She just told me it exists.
Let's do it.
So, in today's episode of Why This Universe, we'll be talking through all of the evidence that has convinced physicists that our universe is indeed filled with this stuff called dark matter. But what do we mean when we say that something is dark matter?
Everyone would agree that something is dark matter only if it doesn't give off any appreciable amounts of light. So we're talking about stuff that doesn't radiate, reflect, or absorb light in any detectable way, or at least easily detectable way.
But since dark matter doesn't reflect or absorb light, we can't see it with our eyes or with any other traditional kind of telescope. Instead, we have to get pretty clever about how to detect this stuff. And that means taking advantage of the one way that we know that it does interact with the stuff in our universe, and that's through gravity.
Let's say you took the planet Mars and just made it entirely invisible, so we can't actually look at it. We could still figure out it's there because we could look at its two moons, Phobos and Deimos, and look at them spiraling around this place in our solar system. And we could infer from the motion of those moons not only where Mars was, but how much mass it had.
And we do that kind of process with things like detecting black holes too, right? Like we can't actually see a black hole. It doesn't emit any light, but we can tell that it's there because of how things are moving around it.
That's right. I mean, black holes, I guess, radiate a little bit of light in the form of Hawking radiation, we think, but we've never detected that. So anytime you hear in the news that we've detected a black hole, what we've really detected is a lot of gravity from a compact object that we infer is a black hole.
Okay, so it's definitely possible to detect stuff that we can't see with our eyes. But we didn't start out looking for dark matter. It surprised us.
So the first evidence for dark matter was back in the 1930s. The astronomer Fritz Zwicky, or astrophysicist Fritz Zwicky, I guess, was looking at a system called the Coma Cluster. So Coma is basically a collection of about 1,000 galaxies, all gravitationally bound together. It's 300 and something million light years away. And he was looking at how fast the individual galaxies in the Coma Cluster were moving. And you can use that information to get a pretty good estimate for the total mass of that cluster. So you can kind of picture like a gravitationally bound collection of these galaxies. They're all moving around at different random speeds. And the faster those things are moving, the more gravity it takes to hold them together. Formally, this is called the virial theorem. It says in a stable gravitationally bound system, the average kinetic energy of the constituents equals the total gravitational potential energy. So Zwicky used this theorem, looked at those velocities, those galaxies, and deduced that the total mass of the Coma Cluster was about 500 times bigger than you would have guessed from the stars alone.
But at this point, people had lots of ideas about what this extra mass could have been, and not all of these ideas were that crazy.
So I don't think it's fair to say that he or anyone else in the 1930s really, thought it was likely that there existed some sort of exotic dark matter. That's not what I think he had in mind. But he thought, well, maybe there's a bunch of cold exotic stars, or maybe there's a lot of gas. Could be things like planets or asteroids or black holes or neutron stars or other kinds of very low luminosity objects like that. He also toyed with ideas that he thought maybe the laws of physics were different in that part of the universe than they are here. Maybe gravity had a different kind of strength, or who knows. So he was pretty open-minded to a lot of wild hypotheses to try to explain this.
But then evidence for this dark matter kept piling up, and physicists started to rule out explanations that weren't working.
Between the 1930s and the 1970s, some astronomers accumulated various other kinds of evidence. They saw the same sort of stuff that Zwicky saw in other clusters, but I wouldn't say the dark matter hypothesis caught fire. It was not something most astronomers took very seriously from what I can tell. But then in the 1970s, it really started to get traction. And this wasn't because of galaxy clusters, but from individual galaxies. So probably the most important work was by the duo of Kent Ford and Vera Rubin. So Vera Rubin was using this spectrograph that Kent Ford built to observe individual galaxies, kind of like the Milky Way, spiral galaxies. And in particular, in 1970, they published the results of their observations of the Andromeda galaxy, our nearest neighbor, a couple of million light years away. And what they were able to do is look at individual stars and gas and see how fast they were spinning in their orbits around the middle of the Andromeda galaxy. And what they expected to find, or what they should have expected to find, was that as you look at stars farther and farther away from the galactic center, they would be moving slower and slower. Just as the farther you get away from a source of gravity, the slower things' orbits tend to be. But that's not what they actually saw. What they found instead is that those stars were moving at about the same speed as you went farther and farther out. The rotation curve was flat. This was also compatible with some earlier radio measurements from the 60s. And throughout the course of the 70s, they and other groups observed a bunch of galaxies, and they all kind of behaved in roughly the same way. And they started to deduce that most of the mass wasn't in the visible stuff. It wasn't made of stars and gas and dust, but something else, something they couldn't see.
And not only that, but this matter wasn't just located at the center of galaxies. This stuff extended way out around each galaxy. We now call these dark matter halos. For example, our Milky Way, our galaxy that we live in, is 60,000 light years across, but the dark matter halo surrounding it extends about 1 million light years across. So that means that our dark matter halo would fit over 16 Milky Ways lined up in a row. And we now know that these dark matter halos formed well before our galaxies did. It was actually the gravity of these dark matter halos that pulled in the atoms that would go on to make the visible parts of our galaxies. Basically, without dark matter, nothing like the Milky Way galaxy would have ever formed.
It started to be noticed that if you took a ordinary spiral galaxy like the Milky Way or the Andromeda galaxy without dark matter, and you just calculated how that galaxy would evolve, it turns out it's not a stable configuration. They should kind of collapse in on themselves and puff up. You shouldn't have ordinary spiral galaxies without dark matter. It turns out that having a dark matter halo around those sorts of galaxies will stabilize them. It kind of acts as a way to hold that structure in place. So that was another thing that kind of came into account at this time. And also just a variety of other dynamical measurements of different kinds of systems were all showing kind of uniformly that if you took all the stars and gas, that could really only account for maybe 10 or 20% of the mass that was out there in the universe. And this was kind of a universal number, whether you were looking at really big clusters or superclusters or individual galaxies. It seemed to be kind of a universal.
So, as dark matter was becoming ubiquitous in all of our measurements of galaxies, new evidence for it sprung up from a very different place.
So in the mid 60s, the Penzias and Wilson had discovered the cosmic microwave background. This is the light that was produced when the first atoms were being formed a few 100,000 years after the Big Bang. And by the late 70s, early 80s, it had become clear that this light, the cosmic microwave background that we're observing from all directions, is incredibly uniform in temperature. It's almost exactly the same temperature no matter what direction you look in. These days, we know that the temperature variations are about 1 part in 10 to the 5, or 1 part in 100,000. So, if I measure 2 different points in the sky, they'll be almost exactly the same temperature with this 1 part in 10 to the 5 variations. And this implies that the density of the universe a few 100,000 years after the Big Bang was also extremely uniform. It was basically the same density everywhere. So we had a very, very homogeneous, smooth universe when it was young. But of course, that's not what our universe is like today. Our universe is very clumpy today. We've got things like galaxies and clusters of galaxies. And gravity is the thing that turns something that's pretty smooth into something that's very clumpy. Clumps tend to get bigger. Things collapse under the force of gravity. But how well gravity does that job depends on how much matter there is. And in around this time, Jim Peebles, who, by the way, won the Nobel Prize in Physics last year, pointed out that given how uniform the early universe was, you would have to have a lot more matter than we could account for with things like stars and gas and dust if you wanted to turn that uniform, that homogeneous universe into the clumpy one we live in today. He deduced that we'd need something like roughly 10 times more matter, basically what we today call dark matter.
So, if you're still not convinced by the cosmological evidence for dark matter, or from the galactic evidence for dark matter done by Vera Rubin and others, there's still one more place to look for convincing evidence, and that's from computer simulations.
And this is in the mid 1980s or so. Cosmologists started to use computer simulations to model how particles would act under, or how collections of matter would act under the force of gravity as the universe expanded and cooled. And you could compare this to the first large-scale galaxy surveys of the universe. So in 1982, the CFA redshift survey provided the first 3D distribution of galaxies in our universe. And you could observe things like this structure you call the cosmic web. So if you back up and look at a big enough piece of the universe, it kind of looks like it's structured like a spider web. So we call it the cosmic web. And you could see it under what kinds of assumptions your computer simulation would give you things like a cosmic web or a universe that looks like ours.
So physicists use these computer simulations to see what kind of matter the dark matter has to be. And they started with 2 categories. The first is hot dark matter, and the second is cold dark matter. So hot dark matter would be particles that are very low mass and travel near the speed of light. And cold dark matter would be massive particles that move much more slowly. So the first particles people tested in these simulations are called neutrinos. So unlike most dark matter candidates, we actually know neutrinos exist, and they're made constantly in interactions mediated by the weak force, which is the one that guides particle decay. And neutrinos have no charge, and they don't interact with light, so they could be a good dark matter candidate that would fall under the category of hot dark matter, the very low mass kind. But when physicists put neutrinos into these simulations, the results that appeared looked nothing like our universe.
Hot dark matter tends to form very, very big clumps, and then those big clumps break into smaller clumps, making things like galaxies. In contrast, cold-moving dark matter particles, slow-moving dark matter particles, form small things first, and then those small things merge, making bigger and bigger and bigger things. It's a kind of a difference between a top-down structure formation sequence and a bottom-up structure formation sequence. And the cold dark matter simulations really do match the universe we see. If you look at the distribution of clusters and galaxies in our universe and compare that to a cold dark matter simulation, I mean, the agreement is spot on. And that gives us a pretty good reason to think that there is a lot of cold dark matter in our universe.
So like Dan said, these simulations show that not only is there lots of dark matter in the universe, but that dark matter is probably in the category of cold dark matter, which means that it's probably a more massive particle that doesn't move quite at the speed of light. And since all of these pieces of evidence, our observations have only gotten more precise and more accurate, and they still show the same thing.
These days, we live in something that is often called the age of precision cosmology. We have a ton of data, and the data is remarkable in its quantity and its accuracy and its precision and in its variety. We have an enormous body of data to draw on, is what I'd say. So this all started in the early 90s with a satellite telescope called COBE. And for the first time, it was measuring the temperature variations in the cosmic microwave background. This is that 1 part in 10 to the 5 I talked about before. But not only did they measure that number, but they started to make maps telling you exactly what those variations look like. And this continued with other experiments or telescopes like Boomerang and WMAP and Planck. These days, SPT is an exciting one. And eventually they're going to build something called CMB Stage 4. All these are going to just keep telling us more and more about our universe. When you combine that with our understanding of the distribution of matter in our universe, the large-scale structure of our universe, and you combine that with the abundances of various light elements like deuterium and stuff that were formed in the Big Bang, and measurements of how fast the universe is expanding over time, and you put all of this together, a really, really remarkable thing happens. You find that they all tell the same story. They all lead to the same conclusions, not only about how our universe has changed and evolved, but about what is in our universe, what has driven it to change and evolve in the way it has. So the kind of the standard simple cosmological model we use has just a few free parameters, like there's how many atoms there are, how much dark matter there is, how much dark energy there is, which we haven't talked about, but maybe that will be a subject of another future podcast. The geometry of the universe, and that's basically it. And all of these different ways of measuring the universe give us the same numbers for all of these quantities. So if we had never observed the cosmic microwave background, we'd still know dark matter exists. If we had never observed the large-scale structure, we would still know dark matter exists. If we had never measured the light element abundances, we'd still know dark matter exists. And if we'd never observed how fast the universe has been expanding, we would still know dark matter exists. They all point to the same conclusion in totally different ways. It is truly an overwhelming body of evidence.
Basically, what you're saying is that there's a lot of evidence from all different places, from cosmology, from the evolution of the universe, from just the astrophysics of measuring what galaxies are like and how much mass they have. And all of these different things are all telling us that dark matter exists, and also that it's probably not just planets and gas, right?
Yeah, there just aren't enough atoms in the universe to put them in any configuration and account for the dark matter. We know from some of these observations I talked about that there just really aren't that many atoms in the grand scheme of things. So you can't take things that don't exist and make them heavier by putting them in different order or something. There just isn't enough there to start with.
Okay, so I know what you're thinking. I get it. Dark matter exists. I'm convinced. Just tell me what it is already. And, well, apologies in advance.
So we don't know. That's the honest answer. We have a lot of ideas for what dark matter might be, but we don't have enough evidence to be sure that any of them is right. So we have a bunch of different ideas. A lot of them fall into this category of what we call WIMPs, or weakly interacting massive particles. We have a lot of different theories that include particles that only interact through the weak force and gravity and were formed in the early first fraction of a second after the Big Bang. That's a possibility. But there are other, even more exotic ideas that with very, very feebly interacting populations of particles. These days, people like us work on things like hidden sector dark matter models. People work on things called axions. People work on stuff called sterile neutrinos. The list goes on and on and on. And until we have experimental evidence that points to some of these ideas over others, we're just going to keep brainstorming.
This episode was produced and edited by me, Shalma Wegsman. Research and writing is done by Dan Hooper and I. Dan is a theoretical physicist at Fermilab and the University of Chicago, and is the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. All music in Why This Universe is produced by Jake Kleinbaum. Thank you so much for your support and for listening, and we hope you tune in next time to Why This Universe.